So for this problem, what we're basically doing is we want to find the ratio of the output voltage over the ratio of the input voltage, assuming that this is an ideal op-amp as modeled in figure A right here. So before even looking at the equation, what we're going to do is we're going to apply the first two golden rules of op-amps, which is, for the first one, that the voltage of the negative terminal, or I'm sorry, rather the current of the negative terminal is equal to the current of the positive terminal, which is equal to 0. So no current is flowing into the negative or positive terminal of the op-amp. The second rule is that we make the assumption that the voltage of the negative terminal of the op-amp is about equal to the voltage of the positive terminal of the op-amp, which lets us assume that the difference between the two is exactly equal to 0, or rather that they are the same. So after applying these two golden rules, what we can do is we can transform the circuit figure of A into the equivalent circuit figure in B. The main difference between these two being is that this node A here that we can create. And so what we did here is we pretty much visualized ourselves disconnecting this node from the op-amp, or severing its connection between here and the negative terminal, since we can assume that no current goes in there. So what you only have is current going to the left and current going up into node B from this node A. Not only that, but it's also virtual ground, because we said that from the second golden rule, we can assume that the voltage of the positive terminal, which is connected to ground, is equal to the voltage of the node A here, which is equal to ground as well, creating a zero difference between the two. So after doing that, what we can start to do is we can start to solve for our unknown, which is our ratio of the output over the input. So since we have two unknown variables, what we need is two equations using both variables that relate them. And so what we can do is we can use Kirchhoff's current law, or KCL, on the two nodes A and B in order to solve this, since they both include variables V input and V output. So looking right here, this is the KCL equation that we get from looking at node A, and we can see that 0 minus Vi over 10,000 ohms plus 0 minus V over 100,000 ohms is equal to 0. And after doing a little bit of algebra here and simplifying it, we finally get that we can make the relation that the voltage of node B is equal to negative 10 of the voltage of the input, which is extremely important, because when we do our second KCL equation at node B, what we have on the next page is we can use this relating equation and directly substitute it in for every instance where we see VB in the second KCL equation. And after doing this on the second line, we get this form of the initial KCL equation. And then after applying a little bit more algebra, particularly splitting up the two terms of the negative 10 Vi minus V output in the third term into two separate terms, and then multiplying both sides of the equation by 100,000 in order to just make it look a little bit more simple, what we can do is we can add up the like terms, which are the negative 10 Vi, the negative 100 Vi, the negative 10 Vi, and then the negative V output. In doing so on the next line, we get the equivalent equation of negative 120 Vi is equal to V output. So then, in the last step, we simply divide the left side of the equation and the right side of the equation by Vi, which gives us the ratio that we are solving for if V output over V input is equal to negative 120, which is the gain of the original op-amp from diagram A. And that's how you solve this problem.